All right, in this virtual lecture, we're going to jump back into chapter 6 and just mostly wrap things up. Maybe one more. Sure, I'm not entirely sure actually. So I know um, Professor Milas started chapter 6 with you that one Monday I was gone. So I want to just, but I just want to quickly review. I'm not going to go through any of the examples, as I'm assuming that he went through the examples, but I just want to quickly review what might have been caught. So let me share my screen. So I'm just going to work through the book for a moment. So let me see. So yeah, so chapter 6 it might seem unusual because it might seem odd that there's this whole chapter 6 in this book, and that's because in chapter 5 we spent quite a bit of time defining trig functions, and so maybe feel like, well, why are we defining the trig functions again? So um, this chapter is on an entirely or somewhat different approach to defining the trig functions. But it will turn out that the unit circle approach that we learned in chapter 5 is equivalent to um this approach we're going to learn in chapter 6. And I think maybe he even already introduced uh the trig functions. So yeah, the definitions might appear different at first, but they end up so yeah, when you define the trig functions via the unit circle approach, and when you try and define trig functions via the triangle approach, the definitions might seem just slightly a bit different than these when you compare these two chapters, but they end up being the same set of functions. These are two different approaches to give you the same set of functions. Um, so for this, we need to, in order, just as we needed some setup before we could define trig functions in chapter 5, we need some setup before we can define, or I guess redefine the trig functions in this section. So we have to talk about angle measure, and I know you went over this, but I just want to quickly review since maybe it's been a bit. Um, yeah, so angle is just two rays with a common vertex O. And then, I mean, as it says here, we have to interpret an angle as a rotation of R1, ray R1 onto ray R2. So it's like you're rotating it. This is all just like a ways of conceptualizing it, but really an angle is just two rays with a common vertex. That's it. And you can think about it as like, oh, I'm forming this angle by rotating these. But I mean, that's not strictly speaking part of the definition of what it means to be an angle. So that's an angle, and in mathematics, we want to have just as in most things in mathematics, we want to have like numerical measures of things. We want to have numerical invariants and measures that we can associate to things we define in mathematics. So we talk about angles, so that it's natural to talk about angle measure. How do we measure these angles? So yeah, here are two angles. So it says, let's see, R1 is the initial side, R2 is the terminal side of the angle. I see the rotations clockwise, the angle's positive. Sorry, counterclockwise, the angle's positive. And if the rotation is clockwise, the angle is negative. So angle is a pretty simple thing. It's a simple definition, and there's ways of conceptualizing it. And now we want ways of measuring it. And so this definition actually helps us to measure angles. So we're all used to measuring angles with degrees. It turns out mathematically, degrees are fine. There's nothing wrong with degrees, but degrees are not as natural set of units. So there's this other unit that we can use to measure angles, and it's called the radian measure. And this shouldn't be mysterious. There's like, for example, we can measure lengths with various measurements. We have, the system that the US uses, feet, inches, feet, yards, etc. And then basically the rest of the world uses the metric system. So and metric system is a lot more natural in lots of different ways. That's easier to work with mathematically. So mathematically, we use the metric system, and in science as well. It's a more natural measurement system. And we have degrees, and that's like something we use in everyday life. But the more natural measure of angle is radian. And this definition is actually a neat definition. It gives you a way of actually measuring. So not only does it define the radian measure, but it gives you like a prescription on how to measure it. So this is how you do this. So you have a circle of radius 1. So first of all, you start with an angle, okay? So you start with an angle, like see right over here in figure 2. The angle, remember, it has a vertex and two rays coming out of that. Let me maybe actually use pencil. So you start with, oops, you start with an angle. So here's our vertex, and then here's this one ray, and here's this other ray. And we want to give a measure, we want a way of measuring theta. We want to be able to talk about, we want to be able to have a way of measuring angles that can be like reproduced. And so the idea is, well, you say you start with this angle right here, and then, remember, rays go off to infinity, right? But if you have a protractor, the definition doesn't reference a protractor, but if you had a protractor, you could set the protractor to have radius 1, and then you put the one of the, I don't know, I guess it's a foot of a protractor. I don't know. The one pointy end at the vertex and the other pointy end, say here, so that it's at a radius of 1, and then you just uh, spin the protractor around. You'll draw a circle with radius 1, and the vertex is at the angles at the center of this circle that you draw. Then by definition, by definition, why isn't this going away? Let's see. The the measure of this angle by definition is going to be this length right here. It's going to be an arc length. So actually, this should sort of sound familiar when we looked at the unit-circle approach. Remember, we started with the unit circle, and we wanted ways of measuring, like imagining ourselves living on the unit circle and then walking around it. We used arc lengths to measure the distance from a given fixed point. So in this case, angle measure just is arc length. And it's sort of this observation that ties these two different approaches of defining trig functions together. So this definition it does two things simultaneously. It defines the radian and it tells you how to measure it. And so this is a really nice definition, actually. This gives you a way of measuring the thing it's trying to define. So yes, you start with an angle. Angle is these two rays right here with a common vertex. Put the one pointy end of your protractor at the center, at the vertex, and that'll be the center of a circle you're going to draw of radius 1. And then you put the other pointy end out at a distance such that it's radius 1, and you draw this circle. And then this length right here that you measure right here, that's the arc length. That arc length is the radian. All right, so let's move on. So I don't think there's actually much more I need to do. Oh, so now we're familiar with we're more familiar with degrees, so it would be nice to have a way of converting angle measures angles measured in radians to degrees, so we can get a sense of what these radians represent. So as it says here, the circumference of the circle of radius 1 is 2 pi. So if you complete a revolution, so a complete revolution has a measure of 2 pi radians. So like you can imagine if you start right here, actually, yeah, I guess it doesn't matter. You start right here, so you fix some point. This will be the initial side of your angle, and then you just rotate this out all the way to here. You will so now by definition when you look at the arc length that you just drew out, that's going to be 2 pi. It's going to be the whole circumference. So 2 pi is going to correspond to 360. So yeah, it says right here we get this simple relationship between the angles, a way of converting, I should say. So we have that 2 pi radians. So I don't like how, well, that's right. I wasn't using it. I was using the other one. Anyways, I was using a different PDF viewer. That's why the pen looks much different. So we have 2 pi, sorry, radians. So 2 pi radians is equal to 360 degrees. And then of course, when you divide by 2, you get pi radians is equal to 180 degrees. And again, should look familiar. This is kind of what we found um, when we were doing the unit circle approach. We found that if you start at that fixed point 10 and you travel pi units around the circle, you travel halfway around the circle. And so in other words, that's the same thing as rotating 180 degrees. Honestly, this book is kind of annoying for doing this, having 2 chapters on trig. I feel like a lot of this could be combined. And I feel like that's probably why I usually run out of time near the end, because like there's just this unnecessary chapter. But anyways, that's how the book wants to do it. This is the book we use, so unfortunately we have to do it this way. But really, these two approaches kind of can be combined. There's no need to have 2 separate chapters. So this should give you a sense. So 1 pi pi radians corresponds to rotating 180 degrees, so halfway around the circle. If you take half of that, you get pi over 2. Is pi over 2 radians is equal to 180 degrees. Let me just write that out. So pi over 2 radians is going to be equal to 182 divided by, sorry, 180 divided by 2, which will give you 90 degrees. And that makes sense. Like when we were doing the unit circle, like say that's the point 0, 1. When I said that you travel pi over 2 radians, that's the same thing as traveling a quarter of the way around. And that just looks like a 90-degree angle. This is definitely just a 90-degree angle. All right. So that's so we looked at how you define the radian. We not only do we give you a way to define it, we will also give you a way to measure it. And now we have a way of converting between degrees and radians. So I'm going to skip these examples. Standard position. This is just more or less like if I give you an angle, just set up your coordinate system X and Y so that the X-axis is always the initial side of your angle. So it's like you start with an angle, it's just kind of free floating in space, and then you just fix it, and then you just make you just make the initial side the X-axis. And this is going to make measuring things a lot easier, and it's going to make the approach, the unit circle approach, that is just basically this is like repackaging the unit circle approach. That'll be clearer when you do this. Put angles in standard position. All right, so I'm going to skip the rest of this. This is not going to come up a whole lot. Uh, I doubt it's even going to come up on the exam. So this length of the circular arc, I mean, it's not that bad, really, honestly. This is just, yeah, I'll just leave it at that. I think he went over it anyways. I just want to go over the basics. So now let's see. He should have gone over this too. So now we're gonna start to define these trig functions. They're not fully defined though, because you notice throughout this whole thing, we're gonna assume that we are dealing with right triangles. So eventually we'll want to generalize these definitions here. We want to generalize them to triangles that are not necessarily right angles. And that will be really useful in applications. So here are yeah, here are the definitions. So opposite divided hypotenuse. So they're pretty simple to figure out to compute. I mean, you have to have a lot of data to compute them, but they're not that hard to compute. Um, and so the example, oh, this is just a useful table. This is kind of like the unit circle basically that I drew. And you can see the correspondence. So a 30-degree angle corresponds to pi over 6. And we know that pi over 6, well, the sine is 1/2, cosine is 3 pi over 2, right? Or sorry, root 3 over 2. Jeez. Um, so this is kind of again showing the connection between the unit circle approach and the right triangle approach. So this is um I don't think you really need to memorize this table. Just memorize the unit circle and then just memorize the unit circle and the conversion that pi radians is equal to 180 degrees. And I'm just gonna stop sharing for a second. All right, let me share my screen again. So yeah, I wouldn't really memorize this table. I would just memorize the unit circle and then remember this conversion right here. Whoa, I don't know what's going on here. Hold on, let me stop sharing and let me get the right browser up or the right PDF. All right. Okay. All right. As I was saying, I would not, yeah, memorize the the unit circle. I mean, I wouldn't memorize this table. I would just memorize the unit circle and that the fact that 180 degrees is the same thing as pi radians. So that will be able to that will help you convert between these two tables. Because this table is kind of essentially, I should say that this part of the table, the measure in radians, and this right here is contained in the unit circle. Because yeah, it'll actually become clear when where's the definition? Let's see. No, I don't think it's in this section. Oh, okay, it's actually in the next section. So, all right, so this is now then I don't think he covered this. So now we define the trig functions for right triangles, and now we want to define the trig functions for any angle. And to do this, we take a given angle, this one right here, and we put it in standard form, like so. So the angle is still theta, the measure of this angle is still theta. And you see that so yeah, we have by the Pythagorean theorem, we have that the radius is given by this because x squared plus pi squared is equal to r squared. So you just take the square root of both sides, and that will give you this length right here, the measure of that, the hypotenuse. And then we can define the trig functions more generally. So you start with an angle in standard position. So like in this figure right here, part B. And then you take a point. So when um you have an angle, you have the initial side, and you like rotate through, and when you stop rotating, when you've rotated theta units, it's going to land at some point in the plane, and you call that point x comma y. So given an angle, you rotate through the angle, it's going to determine a point pxy in the plane, and this point has to lie on the circle on a circle, right? It's going to lie so pxy is going to lie on circle centered at 0, 0 with radius r. Because well, I guess r could be anything really, honestly. It depends upon how far along the x-axis you go. So if you take a point and rotate there, you might end up here. But notice they'll all be on this, all the points will be on the same ray. So depending on where you take your point on the x-axis and you rotate it, you could be on this point, you could be this point, or you could be some point further along, but they'll all be on the same ray. And so that means like, yeah, the x coordinate will increase, but also the y coordinate will increase by the same amount. So their ratio will be the same. So when you take the ratio of the x and the y coordinates, yeah, it'll be the same. So if you take the ratio of these x and y coordinates, and then take the ratio of these x and y coordinates, take the ratio of these x and y coordinates, any point along this ray, these x and y coordinates, that ratio is going to be the same no matter what point you take along that ray. So these functions will be well defined. In other words, it doesn't matter what point you take along the ray, you're going to get the same number. Right, let me clean this up a bit. So, so to define these, you take, just to start over, you take an angle, you rotate, so you take the x-axis, that's going to be your initial side. You rotate the x-axis, theta, an angle of theta. This will give you another ray in the xy plane, say like this right here. So they rotated the x-axis through this angle right here. And then you got all these points along this ray. You could just take any point you want. It doesn't matter which one. You're going to get the same ratio. So you take a point, say this point xy, and then you define the trig functions as follows in terms of that ratio. And as I said, it's let's say, let me just make that observation note. The definitions of the trig functions, this just summarize what I said out loud, are independent of the point x comma y you choose on the terminal ray, I think we call it. So you have an initial ray, you have the terminal ray. So the initial ray is the x-axis, you rotate it theta units, and then you get this ray right here, the terminal ray. And you take any point along that ray and then take the ratio of the x and y coordinates, or take the ratio of the x coordinate with r, so like right here, or take the ratio of the y coordinate with r. It doesn't matter, you're going to get the same answer. The ratio is going to be the same. So now with that in mind, you take so yeah, so the sign is y coordinate over the the radius of this circle, or like how, yeah, it will be the radius of a circle, but just in other words, just the distance from the point on the ray x comma y to the origin. That's what r represents. It's going to also just be the radius of a circle. Now note, what happens when r is equal to 1? So when r is equal to 1, you're talking about the unit circle. And so you get that sine theta is equal to y, cosine theta is equal to x. And I'll just stop there. And these recover so what this shows is that when r is equal to 1, i.e. unit circle, when we're looking at a unit circle, this is terrible right here. Let me put it down a little bit. So when r equals 1, i.e. we're talking about a unit circle, we recover definition of trig functions. I don't know if you can see that. That's killing my eyes. From chapter 6. Or sorry, chapter 5. We're in chapter 6. We get the unit circle approach to the trig functions. And so this theta value is really just that parameter I was talking about, t. So arc length and angle are the same thing. That's the whole point. That's the key takeaway. And this theta is basically playing the role of that that t parameter I was talking about. Oh yeah, here's the whole point. Yeah. I mean, I already studied the trig functions defined using the unit circle. You can see how they're related. You start with the unit circle, and so yeah, I can give you a t value, and that's gonna say, oh, walk along the unit circle that many units, and you land here. But at the same time, um, that point right here, like you can also imagine that point is the result of taking the x-axis and rotating it through some angle theta right here. And then you have this ray right here. Oops. And the point on the unit circle and on the terminal ray is x comma y. And then the definitions simplify right here. So now by definition of the trig functions of the real number t, we have the following. This is unit circle approach right here. But this same point, so there's two ways to get to this point, in other words. You travel along the unit circle of some distance t, or you can think of this point arising from as the result of taking the x-axis and rotating it some angle theta. And then because we're on the unit circle, the hypotenuse, like this is going to be some triangle right here. This r right here is just 1 because we're on the unit circle. So the hypotenuse is 1. So opposite over adjacent, or opposite over hypotenuse will just be the y over 1, which is just y. And adjacent over hypotenuse is x over 1, which is x. So we get the same thing. So now here's just the key takeaway. Angle is the same thing as arc length. If theta is measured in radians, then theta just equals t. They're the same, one and the same thing. So this is how you like connect these two approaches. All right. So here's this table we kind of saw already. So here's this table, one of these trig functions, positive and negative. So yeah, so I'll just give you a second to stare at that, or you can pause it and look at that. And it's not hard to work out why that's true. So the first quadrant, all of them are positive. Why? Well, let's go back to here. So notice R, this number R, that's always a positive number, right? It's a length. So when you're in the first quadrant, your x and y coordinates are both positive. So positive divided by positive is positive. Positive divided by positive is positive. And then here you have x and y are also positive because you're in the first quadrant. So that's why the first row is positive, and the second row, all the trig functions are positive also because you're just taking the reciprocal of a positive number. And for the second quadrant, it just says the sine and the cosecant are positive. So why is that? Whoops, I don't know why that's coming up. When you're in the second quadrant, again, um, R is always positive. So it's the y coordinate that can determine whether you're positive or negative. But if you're in the second quadrant, like you are here, and you like look at your y coordinate, it's some positive number. So positive divided by positive is positive. Cosine is going to be negative because your x coordinate, if you look at the x coordinate, you just like projected down here, it's a negative number. So negative divided by positive is negative. So it's not hard to work out in general what the signs are, depending upon which quadrant you are in. All right, um, so here's an example. Let's see, what else do we have in here? It's kind of annoying, honestly. Working with degrees is annoying. Yeah, so to evaluate these numbers, there's that table you're gonna need, or you can just use the unit circle and convert. So, the idea is now to evaluate, say we want to evaluate cosine of 135 degrees. We want like a reference type angle. So, 135 degrees is a little bit less than 180. So when you rotate the x-axis 135 degrees, you land in the second quadrant, and it determines some point negative xy. Okay. Well, to get the coordinates, well, what is this angle right here? This smaller angle. Well, it's going to be 180 degrees minus 45. And that if you do that, you get 100. Sorry, you get. I'm sorry. Uh, I'm doing this wrong. I want to know what the smaller angle is. So I'm going to subtract 180, which corresponds to rotating to this point here, all the way around the circle. And I want to subtract 135 to get the smaller angle. And that will be 45. So we just need to really know what is sine, a cosine of 45 degrees. And then because the cosine is giving you the x coordinate, um, you just need to throw a negative on there like that. So I think if you go to the table, which is really just the unit circle, right here. So we're looking at cosine of, we're in this row right here. So we're looking at cosine 45 degrees, and in radians, that's pi over 4. And that, oh yes, of course. When you're at 45-degree angle, or when you're at an angle of pi over 4 radians, the x and the y coordinates are the same. Well, we got to throw a negative on though, right? Let's go back to our example here. Because the 45 degrees is like the supplementary angle or whatever. Really what we did was rotate 135 degrees, and it determines the smaller angle of a 45-degree angle. And so get these to get the sine of or the cosine of this angle, we need to look at the coordinates of the point determined by a 45-degree angle. And so for a 45-degree angle, this point right here, the coordinates are root 2 over 2, root 2 over 2. Now, so that means cosine of 135 degrees is negative of the x coordinate. So negative root 2 over 2. All right, so now, okay, so we have this we want to take tangent of 390, but 390 is the same thing as 360 plus 30. So the 360 means at you start with this ray right here, the x um axis, and you rotate all the way around. So that's why you have this red line, this red circle going all the way up to back to itself. and then you got to rotate just a little bit more, 30 degrees. So you actually end up just in the first quadrant. And so a 30-degree angle. So really what we could say then is that the tangent of 390 is actually just tangent of this 30-degree angle. These are, as it says, these angles are coterminal. These two angles, they determine the exact same point in the XY plane. So a 390-degree angle and a 30-degree angle determine the same point X comma Y. Well, what's that point? Well, I guess the easiest way for me is to just convert 30 degrees to radians. So I can go back to the unit circle approach. So this is going to be pi radians over, and actually I should say that when there's no units, when it's just you see a pi or pi over 2, you're just going to assume it's radians. So I'm going to actually get rid of the radians. We don't actually write those units down. So it's going to be to convert, it's going to be pi divided by 180 degrees. And I guess that is pi over 6. Or no, that's not right. Yes, pi over 6. All right. So when I have an arc length or a radian measure of pi over 6, I know that the x and y coordinates for that are going to be um, root 3 over 2, 1/2. Okay. So then tangent is going to be of our 390-degree angle, which is the same thing as our 30-degree angle, is going to be the a y coordinate, 1/2, over the x coordinate, root 3 over 2. So the 1/2s cancel, you get 1 over root 3, and then you can rationalize by multiplying by root 3 over 3, root 3 over 3, and I guess you get 3 over root 3. Root 3 over 3. Is that what they did? Yeah. So that's how they got that answer right there. All right, so it's a little bit more annoying, and honestly, I think that the unit circle approach is way better. Um, so, but yes, I said this is just the book they use, so we got to just do it this way, unfortunately. But the point though, as you can see, is the unit circle approach is easier, so just reduce everything to the unit circle approach. Like convert your, like if I give you an angle, make sure before you do the calculation, just convert it to radians right away. Convert it to our usual measuring system so that you're back to the unit circle and you have less to memorize. Just memorize one approach and memorize how to go from the degree angle approach to the unit circle approach by this conversion factor right here, right? So this is your conversion factor. This will convert from radians or angle degrees to radians. If you want to convert the other way, you multiply by 180 degrees over pi. This will convert a um degree an angle in radians to an angle in degrees. Oops. So this multiplying by this factor, let's say. So we saw that when you multiply by pi over 180, that converts it to, that converts degrees to radians. And when you multiply by this number right here, you convert um radians back to your degrees. But you don't, I mean, I don't think you really want to do that a whole lot. Radians to degrees. Because it's just better to work in radians. Oops. All right, so now there's this idea of a reference angle, and it's kind of like our reference number that we spoke about in chapter 5. So you have an angle, it's an angle in standard position, and then you can associate this angle theta bar, so it's like T bar. Remember the T bar in chapter 5? Um, and it's going to be basically the acute angle formed with the terminal side of theta in the x-axis. So you have, like in the second picture right here, you have the x-axis, you rotate through theta. So now you got these two. Where the heck is it? Um, you have this. Sorry, yeah. So you rotate through theta, and now you have these two angles that you form with the x-axis. So you have this terminal side right here, and you have two angles. You have theta bar and theta, and so you just take the smaller of the two angles, and that's your reference angle. So that's the acute angle that you form, the smaller angle. All right, so now let's see. All right, so we want to find the reference angles for 5 pi over 3 and 187 degrees. So this is going to be in radians right here because you're not when you don't write units, you just assume it's in radians. So what first of all, where does 5 pi over 3? If I rotate that many units, obviously the picture's already showing you, but how do I figure that out? Well, you know that 5 pi over 3 is less than 6 pi over 3, right? Because this fraction right here is going to be bigger because you just increase the numerator by 1. But 6 pi over 3 is 2 pi. So what this says is that when you rotate 5 pi over 3, it shouldn't be quite rotating through the whole circle. You shouldn't quite rotate 360 degrees or 2 pi. So that's why you're going to be a little bit less. And that's why you end up in the fourth quadrant. So 5 pi over 3 is less than, and actually you can say also, so what you have that's true is 5 pi over 3 is greater than 3 pi over 2. And less than 2 pi. So, and 3 pi over 2 corresponds to rotating all the way to here. So you're between this angle, this terminal side and this side right here. So that kind of forces you into the fourth quadrant. So rotating 3 pi over 2 means you land on the negative y-axis. So to get the reference angle, it's going to just be this acute angle you form here. And to figure that out, you just take 2 pi minus, well, they just do it right there, so I won't do that. It's going to be the full rotation, 2 pi, minus the rotation that you actually rotate through, 5 pi over 3. So when you do that calculation, you get pi over 3 as your reference angle. All right, so now, what about this other one? Well, you have this really large angle, and basically to figure out what angle, as it says, this coterminal angle, you want to take 870 degrees. I'm going to write it a little differently. And you want to like break off as many multiples of 360 as you can. And if you do that, you see that 870 degrees can be written as 850 degrees plus 2 times 360 degrees. So how do you conceptualize this? Well, this means you do 2 full rotations, 2 complete revolutions around the circle, and then you rotate by 150 degrees, okay? So that's why and these rotations, these 2 full rotations, they kind of just don't even matter because you end up landing at the same spot. The real the rotation that you care about is this 150 degrees. So that's why these two are coterminal, because you can break off some multiples of 360-degree rotation from the 870-degree rotation. So now where does 150 degrees land you? Well, again, you know that clearly 150 degrees is greater than a 90-degree rotation, which is corresponds to rotating onto up to here, but it's also less than a half a rotation, which corresponds to rotating to so that your terminal side is here. So the only way that's so because your 150-degree rotation is between these two, It forces you in the second quadrant. So to get the reference angle, you need to do um that is this acute angle right here. You have to do the 180 minus the 150, and that will give you the 30 degrees. So that's how you find uh this that's how you find the reference angle. So yeah, so basically like you take your large angle, you reduce it to this coterminal angle 150 degrees, and then once you know where 150 degrees lands, and it's going to land in the second quadrant, you can find the terminal, you can find this acute angle right here, theta bar, by subtracting 180 degrees from the 150. All right, so now they want to use let's see what else we have left in this. Okay, and then the next section is oh, this is annoying. Anyways, okay, because we sort of did inverse trig functions already. This is why it's like we're literally redoing everything, and I feel like you could have done these two approaches like parallel to each other, but it's so it just means more material to cover, which is annoying. All right, so let's go through using this. Let's go through this example to use a reference angle to evaluate trig functions. So we have a sine of 240. Now, we in order to do that, we want to reduce it to an angle in the first quadrant. Remember, there's like these three main angles. So you got like you got pi over 6, which is the same thing as a 30-degree rotation. You got pi over 4, which is the same thing as a 45-degree rotation. And then this last one right here, you have is pi over 3, and that's a 60-degree rotation. So this is correspondence between those. And then there's the point. So these are the angle measures or the arc lengths. And then there are the XY coordinates associated to these. So this is going to be 1/2 root 3 over 2. This is going to be root 2 over 2, root 2 over 2. And then this one right here is going to be, it's going to be the pi over 3 angle coordinates was swapped. So it's gonna be root 3 over 2, 1/2. This is what I mean. Whenever you solve these problems, just immediately write down the unit circle. It's gonna be super helpful. So the angle we care about, so this when you rotate 240 degrees, 240 degrees is bigger than 180. So you go, but it's also less than I guess what would it be 270? Is that right? 93 to yeah. So 180 corresponds to rotating to this side, and 270 corresponds to rotating here. So because you're between these angles, that forces you into the um third quadrant. So the reference angle in this case, theta bar, is going to be 240 degrees minus 180. It's going to be this acute angle right here. So it's going to be 60 degrees. Now, whether you can think of you can evaluate these trig functions using this new approach, or you can evaluate it just using the unit circle. And I just always just think in terms of the unit circle. So we have this 60-degree angle. So and that corresponds to pi over 3. But now, so what we need to do to figure out what sine of 60 degrees is we need to look to the y coordinate, but we need to put appropriate sign on it, right? Because we're in the third quadrant, and in the third quadrant, your y coordinate's negative. So that's why we have a negative here. So we just take negative sine of 60 degrees. The 60 degrees is going to give us the right coordinate, which is going to be 3 pi over 2, but we need to throw a negative on there because now we're thinking about our point as in the third quadrant. Because a 240-degree rotation lands in the third quadrant. All right, so now for cotangent, all right, so first of all, a 490-degree angle, 495-degree angle. Um, let's see, can be written as let's see, I can't even do that in my head, honestly. Let me just think about this for a second. Try to actually pull up the calculator. So you can write the 495-degree angle as a 135 degrees plus a 360 degrees. So 360 we can just ignore. So in other words, what this says is that 495 degrees and 135 degrees are coterminal. They determine the same angle in the plane. That is, they determine the same point x comma y in the plane. So we're going to use that to evaluate this. So the 360 means you rotate all the way around. You do one revolution, and then the 135 means you rotate a bit more. But we know 135 is between a 90-degree angle and an 180-degree angle. So that means you're going to land in the second quadrant. And this reference angle right here is going to be 180 degrees minus 135, which actually is, we kind of did already, is a 45-degree angle. So now we have our unit circle up here. So we're talking about 45-degree angle. That is pi over 4. And we just got to make sure we put the right signs in the right spots. So cotangent, remember, if you're thinking in terms of the unit circle, cotangent is going to be your x coordinate over your y coordinate. So we're looking at cotangent of a 495-degree angle is the same thing as cotangent of 135 because these are coterminal. And that is going to be your x coordinate over your y coordinate. All right. So let's just write those coordinates in. So it's going to be, we're doing 45-degree angle. It's going to be root 2 over 2 divided by root 2 over 2. But that's not the whole story because we got to make sure we put the right signs in. Well, we're in the third quadrant, so that means we got to put, that means the x and, I'm sorry, no, we're in the second quadrant. I'm sorry. Right here, right? We're in this quadrant right here because we're between a 90-degree angle and a 180-degree angle. So in the second quadrant, the x coordinate is negative, so we'll throw a negative on the x coordinate, but the y coordinate is positive, so there's just a positive there, or you can just kind of delete that. You don't need that. But the point is that the x coordinate is negative. So we have a number divided by itself and then a negative, so it's just going to reduce to -1. So that's how they got this -1 right here. Again, I would just convert everything to a unit circle problem because working with degrees in these triangles is really annoying. All right, so that's why that is true. This line right here. All right, so let's see. All right, so this is kind of more of the same thing, but now we don't have to worry about working with degrees and converting and everything. We're just already in radians, so we can just directly view everything in terms of this unit circle approach. All right, so we have this pi over 6, 16 pi over 3 over 3. So we want to view this as coterminal, so to some smaller angle. And it's going to end up being 4 pi over 3, but let's see why. So we can break off let's say 15 pi plus pi, and then divide by 3. And then we can divide, I don't know if that's the right, is that what I want to do? Maybe I don't want to do that much actually, because that would be confusing. Let's say, let's see, maybe actually 12 pi, yes, 12 pi plus 4 pi, divide by 3. So now when you divide the 3 into the 12 pi, you get 6 pi. And then you have plus 4 pi over 3. So this 6 pi means go around, I won't write it down, but the 6 pi means you're gonna go around the circle 3 times, right? Because it's 6 pi is the same thing as 3 times 2 pi. And 2 pi means go around the circle once. And if you have 2 pi's, it means you go around the circle 3 times. So this implies that you can just ignore the 6 pi and it will say that 16 pi over 3 and 4 pi over 3 are coterminal. That's why this first sentence is true. That's why they're coterminal. Because you can break 16 pi over 3 in this way. Break it up in that way. All right, so now where does 4 pi over 3 land us? Land. Um so what quadrant is 4 pi over 3 in? Well, it's gonna be in the third quadrant. It's gonna be in quadrant 3 because 4 pi over 3 is just a little bit bigger than pi. So you land, yeah, so it shows here, you're a little bit bigger than pi. So 4 pi over 3 is just a bit bigger than 3 pi over 3, which is equal to pi. And, but it's also going to be less than 3 pi over 2. So you're in the third quadrant. So now what's the reference? So we found the coterminal angle. Now we want the reference angle. And to get the reference angle, you just do this computation right here. You do 4 pi over 3 minus pi, and it gives you pi over 3. So now in terms of the unit circle, which is, I guess, up here, we're looking at pi over 3. So we're looking at this one right here. And but so when you take sine, or was it, we're doing, yeah, we're doing sine of pi over 3. Sine of pi over 3 is going to be the y coordinate. It's going to be this right here, root 3 over 2. But we're in the third quadrant, right? Right here, we're in the third quadrant. So it's going to be, you make sure you have a negative there. So sine pi of 16 over 3 is equal to sine pi of 4 pi over 3 because, as it says here, these are coterminal angles. And now sine of 4 pi over 3 is going to be equal to negative sine pi over 3. We need that negative because we're in the third quadrant and the y coordinate is negative. And then sine pi over 3 is just root 3 over 3 because that's just something you got to memorize. It comes from the unit circle right there. All right. I'm just gonna skip that because it's kind of more or less the same, everything we've been doing. And then we have these trig identities. These are literally the same trig identities that we saw in the other chapter. So I'll just give you a second to look at that, and there's a proof of it. So you have the Pythagorean theorem, or more generally, the Pythagorean identities. This one's the Pythagorean theorem. These actually follow immediately from the Pythagorean theorem. But collectively, they're called the Pythagorean identities. All right. Let's see. Oh, this is just using them. Okay, that's good. All right, so we want to express cosine, a sine in terms of cosine. Oh, okay, yeah, sure. Um, So by the Pythagorean theorem right here, you can subtract cosine squared from both sides. So it would be 1 minus cosine squared, and then take the square root to get this, and you got a plus or minus. Um, and it's depending upon what quadrant you're in, you're going to use either the plus root or the minus root. So it says, as it says, if I give you an angle and you rotate through it and you land in either the first or the second quadrant, then the sign is positive, so you better take the positive root. So we took the positive root here. If the angle I give you is such that when you rotate through it, you land in the third or the fourth quadrant, sign is negative, so you better take the negative root like we did here. Express tan theta in terms of sine theta. Okay, yeah. So now we know, so by definition, tangent theta is sine over cosine, but we know cosine can be written in terms of sine right here. Basically do the same. Well, actually, sorry, not from that. The cosine can be written in terms of the sine theta by going back to the Pythagorean theorem and doing basically the same manipulation. Instead, you subtract sine theta from both sides and then take the square root. That's how you get this equation right here. And then let's see. Does it say which quadrant they? Oh, you're in the second quadrant. Okay. So now you're in the second quadrant, so the cosine is negative, so you better take the negative root. So that means tangent theta, which is by definition, sine over cosine is now equal to sine theta over negative 1 minus sine squared theta. So this is a way of writing tangent theta completely in terms of sine, which may or may not be useful. All right, let's see. So we got this. A lot of nonsense. All right, so we're given that tan theta is equal to 2/3, and we want to find cosine. And we're in the second quadrant. So we're told, so tan theta. Oh, okay, yeah, I see. So recall the Pythagorean identity is that tan theta, tan squared theta plus, or no, not plus. I believe it's plus 1 equals secant squared theta. Plus 1 is equal to secant squared theta. So we can solve for secant squared theta. And it's already solved for it. Oh my gosh. I haven't had my coffee yet, so don't blame me. I'm gonna actually make some soon and finish after I make it. So we can actually just take the square root right here. And we're in the okay, let's just take the square root first. And then we get plus or minus square root of now tan is 2/3, so it's gonna be 2/3 squared plus 1. And plus or minus. Eventually, we'll be able to rule out a plus or minus since we're specifically given that we're in this third quadrant. And then let's see. So that's going to be 4/9 plus 1. And then that's going to be equal to 9/9. So I guess, wait, what? Oh, yeah, 13 over, yeah, sorry, plus or minus square root of 13/9. But now we can take the square root of 9. So we get square root of 13/3. Now, in the first third quadrant, secant is negative. So secant theta negative in the third quadrant. So that implies that we want to take the third root. So the negative root. So geez. So secant theta is going to be negative uh root 13/3. But by definition, cosine is the reciprocal. So cosine theta, you just flip it to get -3 over root 13, which is actually what we have right here. So that's how you can use a one of the trig identities to solve for one trig function in terms of the other. So I'm not going to do this one. You can work through that on your own if you'd like. It's something we've kind of already done. In fact, the example I just went through is actually something we already did. Um, yeah, so I just used, for that problem, I used this identity together with this identity right here. Use those to solve the problem. That's this problem right here. Given tan of theta is equal to 2/3 and you're in the third quadrant, find cosine. Okay. Just give you a second to look at that. Or you can pause it, of course. All right. Let's see. So what is this nonsense about now? Okay, so there's this whole derivation. I guess I won't bother going through it. So we'll just leave it like that. But here's so here this whole going if you go through this whole derivation here, which is really not that long, you can deduce that the area of a triangle with sides length A and B and an included angle theta is given as follows. It's 1/2 AB times sine of theta. So let's see. Here's an example doing that. So you have this triangle. So I guess just memorize this formula. If you want, work through the proof though, that will maybe help you memorize it. So you have this triangle, you have this included angle 120 degrees, and so you want to find the area. So I guess you could take this as A. All right, I guess it really doesn't matter. This would be B. Yeah, I guess we're kind of following their convention there. And then the sine is the angle is sine 120. So we have sine, so the area is gonna be 1/2 A times B of sine theta. So you plug everything in. So you get 1/2 of 10 times 3. So that simplifies to 15. And now you have 120 degrees is less than 180, but greater than 90. So you're in the second quadrant, and your reference angle is a 60-degree angle. So if you remember, so what do we have? Like, let's just quickly draw the unit circle. So our 60-degree angle is corresponds to something like up here. So we have 60-degree angle is the same thing as pi over 3. And the x and y coordinates for that are 1/2 root 3 over 2. Now, so but our 120 degree angle means we land over here. So this is 120 degrees. The reference angle is 60 degrees. So we need the y coordinate with an appropriate sign, but the y coordinate in the second quadrant is positives. So we don't even need to worry about that. It's just going to be sine of 60. There's no negative because the y coordinate is positive. And then so sine of 60 is going to be root 3 over 2 times 15. So that's that. All right, I'm going to stop for a second and then I'll resume in a bit. All right, so the last section I want to look at in this virtual lecture is it's 6.4. So again, this is something we've sort of already done already. We want to look at inverse trig functions, and we did this in chapter 5, and we noted that technically, if you think of the trig functions, like for example, sine or cosine is defined a set of all real numbers, they don't have an inverse, right? They're not injective because they're periodic. The graphs repeat, so they fail to have an inverse. But if you restrict if you think of the trig function restricted to a smaller domain, then you will get something that passes the horizontal line test, and is therefore and therefore has an inverse. So the sine and cosine on the defined on all the real numbers don't satisfy the vertical line test. There's lots of lines passing at infinitely many points. Horizontal, as I think, if I didn't say that, that's what I meant. Um, and we're gonna just basically do the same thing here. So I'll just give you this definition right here. I won't go through the whole explanation, but because it's basically the same thing. These functions again are periodic. They don't really go through that proof in this chapter, but it's the same proof basically. And so we're gonna use the period to restrict the functions down to a smaller domain where we do have an inverse. So we have the sine, cosine, tangent are going to be restricted to negative pi over 2, pi over 2, 0 to pi, and negative pi over 2 to pi over 2, respectively. And when you do that, when you restrict them and you graph these functions, when you graph these functions over these domains, they are in fact invertible. And remember, for for the tangent function, we have to do the open interval right here, right? We can't include pi over 2 and negative pi over 2 because those are asymptotes. Remember, that's where we have division by 0. So, because remember, tangent of theta is equal to sine theta or cosine. And if you plug in pi over 2, for example, in the cosine, you get 0. So you're going to have an asymptote there. Um, okay. And so now the domain, we have these domains and then we have these ranges, and this is this notation. So let's look at some examples of how to calculate these. So basically, so we have, for example, we want to do, if we zoom out a little bit, if I can. So we want to find out what sine inverse of theta is. So it's going to be some angle, so it's going to be equal to some angle theta such that sine of theta is equal to root 3 over 2 and remember, we don't want just any theta. We want theta to be between, well, we have to look at our range here, right here. So it's got to be between negative pi over 2, pi over 2. Well, so we just got to figure out what theta satisfies this equation right here. And if you think about it, hard and long enough, you'll see that theta has to be pi over 6, pi over 3, sorry. Right? So, and then that implies that since sine of theta, so since sine of pi over 3 is equal to root 3 over 2, that implies that sine inverse of root 3 over 2 is equal to pi over 3. All right, so now for cosine inverse, so we have cosine inverse of 1/2 is going to be some angle theta such that theta is in here between 0 and pi, and this angle theta has to be such that, this is the critical part, is that cosine of theta is equal to negative 1/2. So remember, the cosine gives you the x coordinate, right? Cosine gives you the x coordinate. So we're gonna be, so we have a negative x coordinate. So we need to look for an angle or a radian measure or an arc length, however you want to conceptualize this, where the x coordinate is negative, and specifically negative 1/2. Well, that's gonna mean that you have to be in the second quadrant, right? Because these range of angles correspond to the first quadrant and the second quadrant. So that's gonna imply, it's gonna force theta to be equal to so not pi, it's gonna be sorry. Uh, it's gonna be 6 pi. No, 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 that's 6 pi over 7. Actually, no, sorry. 5 pi over 6 should be. Oh, no, no. Whoops. 2 pi over 3. I'm sorry. Um, because we're in because let's draw this picture to see why this is the case. So when if I'm talking about -1/2 x coordinate, that means, and I'm looking from between angles between 0 and pi. I'm talking about the first or second quadrant. Um, I know that pi over 3 gives me +1/2, right? So I need an angle over here to give me that negative. And to find it, will you just do pi minus uh pi over 3? If you do that, because traveling a distance of pi means you go all the way around the circle. But we want an angle that's in the second quadrant. So we want it to be a little bit smaller than pi. So we got to subtract off this pi over 3 because we know pi over 3 corresponds to 1/2, +1/2. And if you do that, you get 2 pi over 3. So that implies that's the angle. That's the angle that satisfies this equation right here. That's the only one that works out right for that. So um what we can say then is because cosine of 2 pi over 3 is equal to -1/2, it follows that sorry, not sine. It follows that cosine inverse of -1/2 must be 2 pi over 3. All right, and the last one is of tan inverse of 1. So tan inverse of 1 is going to be some angle theta such that, sorry, tan inverse of 1 can be equal to some angle theta such that theta is between -pi over 2 and pi over 2. And more importantly, it has to satisfy this equation. Tan theta has to be 1. So now, um, these angles right here, if you draw your circle, they correspond to, like, you start here and you rotate to this point here, or you start here and you rotate to this point right here. So you're talking about, so this range of angles corresponds to first and fourth quadrant, these range of angles. Now, so tangent of an angle is the y coordinate over the x coordinate. If you're in the fourth quadrant, the x coordinate is positive, the y coordinate is negative, so the ratio of them will be negative. So that means we need an angle in the first quadrant, right? And the only way that, and so so this implies right here, theta must correspond to first quadrant. It can't correspond to an angle I can't give you an angle that corresponds to the fourth quadrant because you won't get the right sign. We want x and y to be equal, actually. They have to have the same sign. And then tan equals 1 implies that the x and the y have to be the same. But this implies that we're talking about the point root 2 over 2, and that corresponds to the angle of pi over 4. So that implies that well, it just implies that theta has to be pi over 4. So that implies that tan inverse of 1 is equal to pi over 4, and that's because when you take tan of pi over 4, you get 1. All right, so that solves that part C. I'm not going to do two because it's just a calculator problem. Who cares about that? All right, so I guess these are sort of like an app. These next two problems are sort of application problems. So let's see what we have. We have this triangle right here that we're given. We want to find theta, given that one side of the triangle is 10 and the other hypotenuse is 50. So the the best way to figure out what sine is to use, or sorry, to figure out what theta is just use the sine function because the sine is the opposite angle, that's opposite side divided by the hypotenuse. So whatever theta is, it has to satisfy this equation right here. So whatever theta is, it has to satisfy this. And then we can actually apply sine inverse to both sides of this equation. So apply, or I guess you can just say that if, um, yeah, I guess you could just say that if sine theta is equal to 1/5, that implies that sine inverse of 1/5 has to be theta. So that's how you're gonna find what theta is. In this case, they just use the calculator, I guess. Yeah, in degree mode. So or you could use radians, I guess, if you want. So here's another problem, like an application. So we have this triangle. So we're imagining that this is like our reference point with respect to which we're saying a given side is adjacent or opposite or what the hypotenuse is. So you always have to have, just like when you're talking about the unit circle, you have to have a reference point. When you're talking about a triangle and you want to talk about sides of it, you need a reference point. So the easiest thing to do right here is just to take this. I mean, you could take this as your reference point. That's perfectly fine. Things will be just a little bit backwards, but that's no problem at all. So we're going to be measuring angles and sides with respect to this. We're going to be referring to sides with respect to this point. All right, so we have hypotenuse is 40, one of the legs is 60, and what is it? I guess it just wants to know what is the angle formed by this with the building and this ladder. So this angle right here. And again, we're just going to use the sine function because if we're standing here, then the side opposite to this point right here is this side right here, which we know is 6 feet. And then this, of course, right here, this side right here is going to be the hypotenuse. So sine of theta is going to be 6/40, which I guess is approximately 0.5. And then because of that, that implies that sine in, let's say actually theta, which is what we're trying to find, is equal to sine inverse of six, let's not say a fraction, but say 0.15. And I'm not going to do the calculation, but yeah, it looks like they get 0.8.6 degrees. So that's another example, an application. Let's see what else is what other examples they have. Well, these are kind of annoying, honestly. They're all annoying when it's the end of the semester. Oops. All right, well, let's just do this one. This doesn't probably not that hard to do. So we have a lighthouse is located on an island that is 2 miles off. So this length right here is 2 miles. We have some hypotenuse. We don't know what it is. And we have, oh, so this, yeah, so this lighthouse forms this angle between these points. And it's some length D. We don't know what it is, but it's just some length D. And so we want to, what is it? Express the angle formed by the beam of light and the shoreline. So this is the line between the lighthouse and the shoreline. And then it's going to form, that light is going to form some angle. So we have, um, we don't know the hypotenuse. We could work it out. So the hypotenuse in this case would be, let's call it like say H. So we have d squared plus 2 squared is equal to um h squared. So that implies that h is going to be equal to square root of d squared plus 4. So we could we could use different trig functions to express the um theta in terms of this number d, this variable d. Um, since we now know the hypotenuse, but it's easiest just to use what you're given and not do this extra calculation. But I just wanted to show you that you can do this extra calculation right here. Um, you can actually determine the hypotenuse. So tangent, recall, so if this is where we're standing at the lighthouse, it's going to be the opposite side divided by the adjacent side. So it's gonna I'm sorry. Actually no, wait, I'm sorry. We're not standing. Oh, I don't know what happened. We're not standing. I'm sorry. We are not standing at the lighthouse. We're standing on the shoreline at this point. And so yeah, it's important that you fix a reference frame. So this is according to the problem, we want to fix this reference frame. And so according to this reference frame, this side right here is the opposite side, and this is the adjacent side. So tangent of theta, this theta right here, is going to be 2 divided by d right here. And then, as I say, you can just apply tan inverse to both sides and cancel out, and then get theta in terms of d. And you could, of course, do anything else. You could say you could do sine if you wanted. So sine theta would be 2 over h, but we know that h is d square root of d squared plus 4, so it'd be 2 over square root of d squared plus 4. And so this would imply you can take the inverse sine of both sides of this equation right here. In this case, you get theta is equal to sine inverse of 2 over square root of d squared plus 4. So that would be another way. And this would be the same exact angle as this one right here. These would be equal. And then you could do cosine as well. So cosine in this case would be, I guess, cosine of theta would be equal to d the adjacent over the hypotenuse would be d over h, and that would be equal to d over square root of d squared plus 4, and that would imply that theta is equal to cosine inverse of d over square root of d squared plus 4. But you can see that again, these are all this theta is the same as this theta, which is the same as this theta right here. But you can see the easiest relationship is use tangent. But they're all the same, and I just wanted to show you that you can get all these. I'm gonna skip this one because it's just a calculator problem, and those are not really that important. Anyone can use a monkey can use a calculator, you know? So let's see. What about this one? So this is a decent problem to go over. Let me get this one. Yeah, so let's just do these last two and then call it a day. So we have so in this case we want to take cosine of sine inverse of 3/5. So the best way to do this is to first draw a triangle. So remember, so sine theta is going to be x over r, right? Where r is going to, let's call it h, because I used h before. It doesn't matter. You can say h or r. But h is going to be the hypotenuse, the length of the hypotenuse. So it's going to, sorry, it's not x, it's y over h. Over h. So that implies that sine inverse is going to be y over h, and it's going to be your theta. So we have a theta here, so we draw our theta there. And then what this says is that theta is when you take cosine inverse of the 3/5, the 3 is going to be your y, and the h is going to be your 5. So that's why you put a 5 here and a 3 here. Okay? So that ratio tells you what the sides are. And now, by Pythagorean theorem, you can figure out this 4. Why? Because Let's imagine we don't know what this is. So let's cross it out. We don't know what it is, so we'll call it x. We know that 3 squared plus x squared is equal to 5 squared. This is x squared plus y squared is equal to h squared. And you can solve for x, and it's going to be square root of 5 squared minus 3 squared, which is square root of 25 minus 9. And that's going to be square root of 16, so it's 4. So that's why you get a 4 here. So just to start over again. So first we want to figure out what is sine inverse of 3/5. So they say just give it a name, call it y, and then call it theta, and then theta is going to be some number in this interval right here because that's where the sine inverse function is defined. And the sine of this angle is going to be 3/5. So I didn't write that there. So let me say, so we have that sine inverse sine of 3/5 is equal to this theta here. So that implies that 3/5 is equal to sine theta. And we know that sine theta, sine of some angle is your y coordinate over your hypotenuse, right? That's what I wrote here. So 3 is going to be your y, and h is going to be your 5 is going to be your hypotenuse right there. And then using the Pythagorean theorem, you can work out the other length is 4. So now, so to get cosine of sine inverse of 3/5, we called this theta. So so computing this is the same thing as computing this angle cosine of theta. Now we just need to look to this triangle and figure out what is cosine of theta. Well, we have all the sides worked out so we can figure it out. So it's going to be the adjacent over the hypotenuse, 4/5. So cosine of sine inverse of 3/5 is cosine of theta, some angle theta. We don't know exactly what it is. Doesn't matter. But based on this triangle where the one angle is theta, we can work out what cosine of theta is. It's going to be 4/5. It's going to be the opposite divided by the hypotenuse. There's a second solution. I don't think it's worth going through, honestly. And then, yeah, I don't think this is worth going through either. It's kind of just more or less what we did, but so what we did was of cosine of sine inverse of some number. This is just where the number is now just any general number, and you can go through the same exact steps to work out the general case, but I don't think that's helpful. I think it's helpful for our purposes. We don't need to do that. So that's all. Whoops, I did not want to stop sharing. Because I want to show you one more thing. So that's all. The only thing we have, apparently there's chapter 7 that's supposed to be covered, which is ridiculous. Like, this is way too much material, honestly. So we're not going to go through 7. 7 is not on. The practice problems, none of those problems involve material from chapter 7, so I'm not going to bother going through that unless if I do get the actual final exam and there is a problem, then I'll just go over it then. But I don't think we're going to need it. So all we need now is the law of sines and the law of cosines. So that I will do probably Thursday. And of course, I'm going to post this video now, but I doubt you'll probably watch it right away because you're probably studying for the exam, but I'm just going to post it now for those who maybe do want to watch it right now. All right, so that's all we have left, and then we're completely done.